Now with paper. Okay, just about time to get going. Let's see, I'm still grading. I gave 3 tests last week and I'm only, well, I got the big class done, astronomy, but I'm only halfway through 114 and yours. So this afternoon I should be able to make a lot of headway on those. Anyway, let's see, any questions on either homework or the whatever it is, the resistivity lab? Yes.
Is there a homework posted? Because I didn't see one in the modules.
Oh, shoot. I thought I did. Let me look. Rats. Let's see. Inbox. Oh, wait, that's not where I'm going. I'm going to courses. I know I was working on the Word document for it. Oh, let's see. Let me look in one of the... Did I publish it? Last week was week 5, right? Oh, it's in the example problems and videos for this week. At the bottom of it, it says homework for this week, still missing a question 4. So yeah, it's not in the usual place. I just put it in there and I did find a question 4 for it. I remember typing it, but it's not in there yet. Anyway, I'll post that later today and have to give you more time, I guess, or extend what I had as in mind as the due date. I didn't put a due date on here anyway, so. Okay, yep, more to do. Homework, physics. Physics 223. Okay, yeah, there will be. Okay, well, let's switch over to the IPVO thing here, or whatever it was. Today I want to look at current loops and torques on current loops, and we'll start with a rectangular current loop, and we'll get an expression for that, and hopefully you see paper and a waving hand. So.
Yeah.
Okay, and we'll imagine that we have a uniform magnetic field. It gets really complicated if you don't. And what else will we have? I don't know. A nice rectangular current loop to start with. So we'll just imagine that the magnetic field in some region of space is uniform and pointing upward like that. And then we'll imagine that in this magnetic field, we have some rectangular current loop that I'll try to draw, I don't know, somehow in here. And it's got a nice orientation to the current loop. Yeah, sort of. Well, that doesn't look so good. We'll change our viewpoint, I guess. So if you've got the magnetic field going straight up like this from one viewpoint, the current loop will look like this. And so we'll imagine that this length here is B, and that B, that current loop, makes an angle theta with the horizontal. And so that's one orientation. And then another orientation that we might take is to look down on the current loop so that if you look down on the current loop, the magnetic field will appear to be coming straight at you. So a whole bunch of little eyeballs here. And with that orientation, that B isn't going to look like a B anymore. It'll look more like, let's see, B cosine theta or something like that. But with that orientation, we'll ignore that side of it. And we'll imagine that we've got some little length A that we actually get a true measure of when we're looking at it from this angle. And that'll be the other dimension of the rectangle. And so the rectangle, if you looked at it perpendicular, from a perpendicular direction, it's got two sides of A and two sides of B, but it happens to be tilted like that. So ignore this picture because it's hard to know what's going on there. And the loop is actually made out of wire, some conductor, and we can imagine that it has just a single turn. Turns out the effect we get if you have n turns of wire in the loop, it'll just be multiplied by n. And so we can go with that. So let's figure out for the individual parts of the loop what the force is on each one of those things. And we'll be using our IL cross B thing, whoops, B, not F. The force on each one of those things is going to be IL cross B. Okay, so L is a vector that points in the direction of the current flow. So from this viewpoint, it's easy for me to consider the forces that are acting on the two that go to the right here and to the left there. And I'll number each side, A, B, or letter them anyway, C and D. I guess I could have numbered them as well. But, oh, I started off numbering them, didn't I? 1, 2, 3, and 4. Okay, so side 1. Okay, now the force that's going to be acting on it, B is upward, remember, so if I pick this piece of paper up and rotate it 90 degrees, IL will point in that direction, B is up, and so the force that's going to be on it will be to the right, and I can draw that force in here, although I'll just call it F1, and the magnitude of F1 is going to be I, the length of the current is A, and just IAB is what it ends up being. If I sketch the direction of that force on this diagram here, it'll be in this direction. So here is F1 in that direction, and it has a magnitude of IAB. So there's that. Now F3 up there is going to have a force of the same magnitude. It's the same length, IA cross B, but it'll be in the opposite direction. So F3 is also equal to IAB. But if I draw it on here, it's going in this direction. So this is F3 as a vector there. Okay, well, what about if I imagine that here I'm looking at side 2. So here's side 2. The force on it is, remember, it's IL cross B. So this is the direction of IL here. That's the current flow. And there will be an angle here, which is equal to 180 minus theta between those things. And the force on 2 in magnitude, F2 will equal, well, it's got a length of B, so that's the IL magnitude there. So I little b in this case, and then capital B, and the sine between IL and B, or the angle between IL and B, will be 180 minus theta. So have that. Now, if I could flip my viewpoint, go to the opposite side of this thing, so that need another piece of scratch paper. Over on the far side of this thing, if I look back along here, I would appear to see the thing coming down here. It's got a B is going in that direction. This is theta again, and the current direction is in this direction, and the magnetic field is up still. So now I've got I little b cross whatever it is. This would be side 1, 2, 4, I guess, that I'm thinking about. The magnitude of F4 is going to be the current that's flowing in it, little b, capital B, and this time the sine of, what does that turn out to be? Let's see. This is theta. 90 plus theta, I think. Except something doesn't seem right. Did I get this one right? I think that's 90 minus theta, isn't it? Yeah. Okay. For side 2, because it's this angle here is 90 minus theta. I don't know where I got 180 minus theta. Anyway, it should be 90 minus theta. So side 4 is going to be, F4 is I little b capital B sine of 90 plus theta. Okay, well, if you imagine a graph of a sine curve, so you've got sine theta on the vertical axis and theta on the horizontal. Starts off at 0, at 90 degrees it's this, and then you'd be over here at 180 degrees. And it reaches a peak at 90 degrees, and it's symmetric either side. So the sine of 90 plus theta, if this is 90 plus theta, is equal to the sine of 90 minus theta, despite how I drew it. So F2 and F4 end up being equal forces, and they would act as if they were at the center of each of these pieces. And so here's F2 as a vector, here's F4 as a vector, and they have the same line of action in this case. It's not like the F1s and F3, where they have different lines of action. And you can imagine these two forces, F1 and F3, acting to make this plane current loop flatten out. And so anyway, that's what's happening in that case. But these two, they'd be both of them acting down a line that's right through the center of this particular length. They're acting not in the direction I've got my pen pointing, but that's their line of action. So they share a common line of action. That's what you call it in engineering anyway. So these two forces cancel out, and they do not cause a torque. But these two forces, while the forces are equal and opposite acting on the current loop, their effect is not, because they will tend to make it rotate unless the current loop happens to be lying flat to begin with. But if it's not, then there'll be a tendency for that thing to rotate. Now, how much or what is the value of that torque? Well, this is side B here. This would be B over 2 coming up to here. And the torque from side 3, torque due to force on side 3, if you remember what a torque is, we use that weird Greek letter, tau, lowercase tau, and it's equal to R cross F, where R is the distance from where we're calculating the torque about. It's a vector, actually, that points from here up to here. And then, let's see, what else do we get going here? Oh, F is just the force. So the R in this case is B over 2. And then this will be our angle theta again, I think. And that's the angle between R and F. So the magnitude of this torque is going to be B over 2 times F times the sine of theta. Okay. So that's the torque, but, oh, this is F3 that we'd be talking about. F3 was IAB, and so I little a capital B, I should say. So we'll end up here with I out there, 1/2 B. We'll also get a little capital A in here and a capital B, IA capital B, that's that part, and a sine of theta on that, what we have. Okay, so that'll be the torque due to 3, and I'll have an F3 in here, and I could call this R3 as well. All right, well, what about the torque due to side 1? Tau 1, I could call it. That'll be an R vector that goes from here down to here. It'll have the same angle theta between the R and the F1 vector again. So I'll have the magnitude of an R1 cross F1. And if I calculate the magnitude of that thing, R1 is 1/2 B, so B over 2. F1 is IAB again, I little a b, and the angle between the, what am I saying here? The R vector and the force vector is again theta. And so I have that. Now, both of these torques act in the same direction. They will tend to make the plane of the current loop rotate in the clockwise direction. And so the net torque magnitude ends up equaling, if I add those two together, I just lose the 1/2 is what I lose. And so I'll have I little a little b. We still visible there? Yeah. Then capital B times the sine of theta. Little a little b is the area of the current loop. And so for shorthand notation, I can just say little a little b is equal to capital A. So this will equal I capital A B sine theta. Okay, that's the expression for our net torque, and it turns out we would get the same net torque anytime we have a plane loop in a uniform magnetic field. And I think it's one of the theorems from multivariable calculus, but I don't remember if we did it when we did the class, Nathan. It may have been something that wasn't in that book. I don't remember. But at any rate, turns out it doesn't matter if it's a rectangular current loop or a round current loop or anything else, you always get this. Now, we, because that's the case, we tend to talk about something called a magnetic moment. And a magnetic moment is something that a current loop, just for simplicity, we define it to be something. And we use yet another Greek letter for this one. This is mu. And that's the prefix for a micrometer or micro anything, actually. So mu is equal to the current in the loop times an area vector for the loop. And the way you determine the direction of the area vector is by a sort of pseudo right-hand rule. If this is the area, and the current is flowing in this particular direction, then if you use the right hand, fingers of your right hand so that you can curl them in the direction of the current, then the area vector points in this direction, and so does the magnetic moment. So it points in the direction, A points in the direction of the magnetic moment. You can just think of mu as a vector equaling having a magnitude of I times the area of the loop, and its direction is determined by that right-hand rule. We use, this is, I think, just our second use of the right-hand rule. First was for the cross product. It'll show up a lot of times. Later this week, in fact, maybe tomorrow, when we look at the Biot-Savart law, which is the law that will let us calculate what a magnetic field from a current happens to be, we'll use the right-hand rule in there. It's built into the law as well. So that's something else that we have. Okay. Because we've got this torque that acts on things and we can reorient things in a current loop like this, it turns out there's a potential energy associated with a current loop in an external magnetic field. And the potential energy looks a little different than usual. It ends up being, it's got a minus mu dot B in it. So it's at a minimum when the two are pointing in the same direction, and I guess that makes sense for our sketch that we've got here. If you think about it, the torque that acts on the current loop, if we look at it sideways, it tends to make it rotate in such a way that the magnetic moment will be pointing in the same direction as the magnetic field. So that's something that happens. And if they happen to be opposite each other, it's a point of unstable equilibrium. So if you've got a situation where you have a magnetic moment pointing in this direction and the magnetic field is pointing this way, the net torque on it at this instant is 0, but it's like having a ball sitting on top of a cone balanced perfectly, a little nudge and it starts falling off the cone. And that's what happens if you displace this magnetic moment just ever so slightly from being in the opposite direction as this, there'll be a net torque on it that'll end up flipping it. So that's something that happens. But anyway, there's a couple of new terms, magnetic moment, and it's not bad. By the way, if you have some number of n turns in the current loop, the magnetic moment just becomes NIA. And so it's easy to deal with that. It's as if you multiply the total current by that factor n, and in a sense you are. You've got just a bunch of parallel wires, and if you think of stranded wire, that's effectively what you have when you have a coil, even a single turn of a coil. If each strand of the wire is carrying some amount of the current, they add together to give you a single current. Okay, I just have a couple of example problems on this, and then I wanted to talk about another application of this that's kind of interesting. Another astronomy application, as usual. Here we have the plane of a 5 by 8 centimeter rectangular loop of wire is parallel to a 0.19 Tesla magnetic field. So here we've got, this can be the plane of the loop, and it says it's parallel to a magnetic field. So this is B in this case, and it carries a current of 6.2 amps, which is fairly hefty. Now, if this is the loop, the magnetic moment will either point this way or that way, depending on how we orient it. But no matter what it happens to be, there's going to be a pretty good torque on the thing. So the torque will equal mu cross B. Oh, did I ever? I don't think I ever exactly did that. What we had here, because we had that the net torque on the thing was IAB sine theta, and then we defined the magnetic moment to be I times A, then that'd be the mu thing. This would be mu B sine theta, which is exactly what we have for the magnitude of a cross product. And the net torque ends up being mu cross B. And I forgot to bring that up. So read the section in the book about this. They probably go through something pretty much like the example I did. All right. So in this case, the magnitude of mu, it's a single loop of wire as near as I can tell with a 6.2 amp current. So it will equal 6.2 amperes. Now this A stands for ampere, not the area of the loop. The area is equal to 5 times 10 to the minus 2 times 8 times 10 to the minus 2. We can do that in our heads, and we get 4.0 times, actually we'd get, well, only two significant figures. 10 to the minus 4th, 10 to the minus 3rd. I think it's 4.0 times 10 to the minus 3rd. Meters squared. Better check that. I don't trust myself today. Oh, I couldn't even punch in 5 correctly. Good grief. Yeah, 4.0 times 10 to the minus 3. And that's the area. So mu will equal whatever 6.2 times 4 happens to be. And I get 2.5 times 10 to the minus 2. And the units of the magnetic moment are amp meter squared. So we have that. Okay, the torque acting on the loop then is, oh, we already figured out the magnetic moment of the loop, so that was B. I wonder why they asked in that order, but the torque will equal the magnitude of mu cross B, which, because they're perpendicular to each other, it'll be mu times B times the sine of the angle between them, which is 90 degrees in this case. So that's just mu B. So we multiply that magnetic moment times 0.19 Tesla. And I get 4.7 times 10 to the minus 3. Now, unit-wise, every problem we do here is an adventure in units. We'll have amp meter squared times Tesla, which is amp meter squared. A Tesla is a Newton per amp meter. And so the amps divide out, one of the meters divide out, and I get Newton meters, which is force times distance. Those are the metric system units for torque. And if you have a torque wrench, especially a digital one, you can set it to read either Newton meters or foot pounds, which is the American system unit of torque. And I've got an old mechanical torque wrench that does the same thing, actually. It's not as precise as the metric one, but it works too. So Newton meters for that torque. What is the maximum torque that can be obtained with the same total length of wire carrying the same current in this magnetic field? Any idea how you might get that? We're looking down on this wire loop, and it is, well, not to scale, 5 centimeters by 8 centimeters. The magnetic moment is the current times the area. So we get to use the same length of wire. The only thing you could maximize is the area. Any idea?
Maximizing area means you have to make it square.
Is it square or round? I don't know. We could try it. You've got 26 centimeters of wire. And so let's see, if it was a square, it would be, let's see, 6.5 centimeters square, or 6 centimeters on a side. Oops, have to remember to stick in the E-2 on that. And I get 4.2 times 10 to the minus third meters squared minus third. What did we have? 4.0 times 10 to the minus third. But a circle, let's see, 26 centimeters is the circumference. I'd get a radius of 4.14. And I'm going to leave all the significant figures in here. Yeah, if I make it oh, let's see, I have to multiply that by 10 to the minus 4. Yeah, for the circle, I'd get an area of 5 point to 2 significant figures, 5.4 times 10 to the minus 3 square meters. So, yep, get a little bit more area with the circle. And there's probably some way to show that with drawings, but at any rate, what we would get in that case for C is we'd have 6.2 amps times 5.4. That's if I didn't screw up the calculation. Times 10 to the minus 3 meters squared. I'm surprised it's that big a difference. And then, so that's mu. B was 0.19. I'd get a torque of 6.3 times 10 to the minus third Newton meters in that case. And I think that's all they asked. Yeah, it was just doing something. One of the homework problems I want to talk about at least, and it has a thing where I'm not sure if this is what the exact deal is, but, or the sketch, but it has a current loop that looks like this, and it's supposedly hinged along this particular line. So it's hinged along one edge, and you're supposed to calculate the torque about that edge. And when you calculate the torque about an edge like that, you calculate the torque from any point along this thing, and any force that's acting along this thing will produce no torque, because torque is equal to R cross F, and if either R or F happens to be 0, then the torque is 0. Well, for whatever current, and I don't know if it's flowing down or up in the example or in the homework problem, but if it was flowing down, for instance, and the magnetic field was, I don't know, you could pick a direction, I don't remember what it is, but anyway, there would be a force acting on this thing, but the R vector for the current element along here is 0, so there is no torque along here. It's like trying to open a door by pushing right at the hinge line. You're not going to make much headway on opening that door when you do that. So the parts that do contribute to the torque are here, here, and here. So check those out, and you should be able to answer that question. Okay. Yeah, I think we can get this is a sort of an example for the hydrogen atom, the Bohr model. And in the lowest energy state, the electron orbits the proton at a speed of 2.2 times 10 to the 6 meters per second in a circular orbit of that thing. That's the Bohr radius. If it's 3 significant figures, a lot of times you'll see it written as 5.29 times 10 to the minus 11th meters. What's the orbital period of the electron? If the orbiting electron is considered to be a current loop, what is the current I, and what's the magnetic moment of the atom due to the motion of the electron? And this is something that atoms have been found to have magnetic moments, and they will respond to an external magnetic field, and it turns out that response is quantized, which is one of the unique aspects of things at the atomic level, is that the alignment of the atom with an external magnetic field will take certain values, not just any old value, but only particular values, and they end up being integer multiples or half integer multiples of particular quantities, like h bar shows up again and again in quantum mechanics, and it happens to be Planck's constant divided by 2 pi. When I was writing my thesis, I think I was just about the first, one of the first graduate students at University of Minnesota to use a word processor for a thesis. They were a brand new thing in 1987 and 89 when I was writing it. And my thesis advisor was very impressed that I figured out how to make this symbol. It's called h bar is what it is, but it's just h divided by 2 pi, but it's a pain in the neck to have to write this. But I just figured out a macro. I was writing it on a Macintosh. Oh, what was the model? A really early Macintosh. I can't remember what, maybe it was a Macintosh. I don't know. An Apple computer at any rate. And it had a very early version of Microsoft Word on it, but you could program these things called field codes. So I did that as a kind of a little macro, and I think I just had to go Alt-H, and I would get that H bar in there. And there must be, I don't know, hundreds of them in my thesis. Okay, so that was my big contribution to physics, was figuring out a way to make H bar. Other than that, the thesis went nowhere. All right, in the Bohr model of the hydrogen atom, in the lowest energy state, the electron orbits the atom with that speed. So we just kind of imagine this thing going around here with a radius r sub b. And we'll kind of imagine making a little cross section here and figuring out how much current goes by that thing, how much charge goes by that thing in 1 second. Well, the charge is entirely due to this one electron that's going around there like crazy. So first, the orbital period of the electron. Well, the period is going to be, I take that distance, the 2 pi r sub b, and divide it by the speed of the electron. Because if you solve for the speed, it'd be 2 pi r sub b divided by how long it takes to do that. So let's see, 2 times pi times the Bohr radius. And divide by that speed. One of the objections raised against the Bohr atom, which is kind of based on the Rutherford atom, Rutherford had discovered the nucleus of the atom in around 1910, and plus or minus 2 years. I don't remember which year exactly, but when he discovered it, he said the electrons would be orbiting the nucleus of the atom, the positively charged nucleus of the atom, under the influence of the electromagnetic force, like the planets orbit the sun under the influence of the gravitational force. And people looked at that and said, well, you've got a charge that's traveling in a circular motion, and it'll be undergoing centripetal acceleration given by this expression, and something that physicists had discovered in the 1800s, that is, was that if you accelerated a charge, it radiated energy. And so they said that the radiating electron should radiate away whatever energy it has and just spiral into the nucleus and get absorbed by it, and atoms would exist for just some tiny fraction of a second, measured in things like picoseconds. And so there shouldn't be any atoms, but there are. And so Bohr comes along and he says, well, the electrons are confined to orbits where they have quantized angular momentum, and in those orbits, they don't radiate energy. So everything's explained, except for why. But it was steps along the way. The eventual answer was that electrons don't act like little planets orbiting the sun. They actually, an individual electron spreads out around the nucleus of the atom as a wave. And so it's even weirder than we thought. All right, but we can figure out the orbital period. Now, what good will the orbital period do us? Well, I get an orbital period of about 1.5 times 10 to the minus 16th seconds. But guess what the reciprocal of that is? It's the orbital frequency, which is how many times per second that electron goes around here. And if I have some little cross-sectional area, whatever that orbital frequency is, it's as if you have that many electrons going by through this little area per second. So the frequency is just the reciprocal of that. Whoops, not 0.5, minus 1 is what I wanted, for the exponent on there. 6.6 times 10 to the 15th, and that would be seconds to the minus 1, or hertz. Okay. If the orbiting electron is considered to be a current loop, what's the current I? Well, if I just multiply F times E, the charge on the electron, I'll get coulombs per second. And the effective current is just going to be that, F times E. So 6.6 times 10 to the 15th, second to the minus 1. And the electron has a negative charge, but we don't really care about it. We could think of a negative charge going that way would be a current going that way, positive current going the opposite direction. So 6 times 10 to the 15th, wherever it is, 1.60 times 10 to the minus 19th coulombs. And so it's not a huge amount of current, but it's one little electron amounting to it, or making it. So we're good. And I get about 1.1 milliamps is what it actually comes out to be. And that's one electron doing that. So that's pretty amazing. And then the magnetic moment of the atom due to the motion of the electron. Well, let's see. The magnetic moment in magnitude is just going to be I times A. So it'll be 1.1 times 10 to the minus 3rd amperes times pi times the Bohr radius squared. So 5.3 times 10 to the minus 11th meters. Yeah, we've got it in meters squared. So times pi times not a big number, 9.3 times 10 to the minus 24th, and this would be Newton meters squared, but it's just one little hydrogen atom that has that. So you could see what it'll do in an external magnetic field by playing with that. And you can read about, some of the experiments done in the early 20th century, mostly in the teens and 20s. I think, it might have been Gauss-Schmidt and Uhlenbeck who did the experiment that demonstrated electron spin, if I remember right, which was another effect. In fact, that's something related to what I want to talk about here. So I think that was all there was to that problem. Here's a little section I got out of Wikipedia, and it's about something called the hydrogen line. And in the hydrogen atom, it turns out that from the electron's viewpoint, if you think about it, from the electron's viewpoint, it has a proton going around it. And so it will experience the magnetic field of the proton, and the electron has a little magnetic moment all by itself, even if it isn't kind of creating the magnetic moment for the hydrogen atom by orbiting the hydrogen atom. That one is called the, let's see, I can't remember the term for it right now. But anyway, the electron by itself has a magnetic moment. And we refer to that as electron spin. And it turns out that neutrons and protons also have a property called spin. And it's something that has to be taken into account in all sorts of quantum mechanical calculations. And because it has that spin, the electron will have some spin angular momentum as if it was this little rotating sphere of charge. So it has spin as if it was some little thing like a BB, but other properties of it make it plain that the thing is spread out in space. And at the atomic and subatomic level, things get very interesting. You're constantly having to deal with the wave nature of the particles, electrons and protons and neutrons, but then at the same time, they have these properties that were as if they were little point particles. And so, or a sphere particle, something like that. But in the hydrogen line, if you've taken chemistry, you might have heard about the electron energy levels. The lowest one is minus 13.6 electron volts, and then there's a bunch of them. They get closer and closer together. And once you get up a certain ways, the electrons are very loosely bound to the electron and can get knocked out of it. The visible light that hydrogen gives off happens when this is the n equals 1 level, n equals 2, and don't worry about those numbers. They show up in a formula. But anyway, the visible spectrum of hydrogen occurs when electrons fall from higher energy levels down to this n equals 2 level. And the spectral lines that you can see, and the term line is caused by, it's an artifact of the thing you're looking at them with, which is a diffraction grating typically. But that's what they call spectral lines. And this set of spectral lines are called the Balmer spectral lines, or the Balmer series. And this lowest energy level is actually split in two because the electron is experiencing a magnetic field, that of the proton, which appears to be orbiting around the electron from its viewpoint. And so it can have a magnetic moment that is misaligned with the magnetic field of the proton or aligned with it. And the lowest energy state is when it happens to be aligned with it from that minus mu dot B thing. Now, this transition is called the hyperfine transition, or it splits the this energy level into two parts. And the transition from one orientation to the other orientation is extremely unlikely. Oh, let's see if I still have, oh, here it is. It's mentioned here somewhere that in this Wikipedia article, it's highly forbidden with an extremely small rate of 2.9 times 10 to the minus 15th seconds, which makes in quantum mechanics, everything is a probability, but it makes it have a lifetime of around 10 million years, this particular state. And so we just don't see it happening on Earth because we've already got, even in a good vacuum, we've got too many particles in there. But in space, it happens all the time because there are enormous clouds of hydrogen out there that are of very low density, and the electrons might go many centuries without colliding with anything. And so you actually can see it in space. And it's a way that they map the presence of hydrogen in space. And it's taking advantage of this mu dot B, this particular, it's got a minus sign in there, that energy. And if the electron changes, it gives off a photon. In this case, the photon has a long wavelength of, here it is, 21 centimeters. It's called for short, although I found out that the radio astronomers who detect it actually refer to it by its frequency, which is about 1420 megahertz. So some other stuff beyond the scope of this course, but it's an application of the torque on current loops, more or less. So that's probably enough for today, and I'll get that homework assignment posted up there today. So, but you can access it. I need to fix question 4, which I think I've got fixed on the typed version on my computer, but I'll upload that so you'll have the whole set, and I'll have to probably make it due next week, which is going to be hard. You may have a stack of 2 homework assignments going on at the same time, but one of them I'll make due late next week or something like that. Okay, any questions? All righty, I'll turn you loose.